We are familiar with representations of all kinds. For example, letters represent sounds, or bit strings represent computer files. So, for example, if I give you some random bit string and I tell you, hey, this is an image, then that is not a problem. You can basically apply some encoding scheme that we agree upon, for example, JPEG or PNG, and you get an image. Or the same bit string, for the same bit string, I could tell you, hey, this is an audio file and you should apply MP3. Again, no problem, you'll get a sound file. So there's nothing inherent in the bit string that will tell you what it is about. So we can call this kind of mapping or this kind of representation ambiguous. Its content is entirely dependent on an externally defined decoder. So there's no issue with this. However, when it comes to conscious brain states, I would say we're in a very different situations. So if we assume that consciousness supervenes on brain states, then we are in a situation where a neural state has to unambiguously map to a set of conscious contents. For example, if a certain brain state corresponds to a person who is perceiving only a red square, that same brain state cannot be said to alternatively also encode the conscious experience of only a green square. Now, why is that? That's because consciousness is an intrinsic property. And here, just to also disambiguate how I use the term consciousness, I want to use it in the sense of phenomenal consciousness. So the what is it likeness of a certain brain state. So here we have fundamentally a different situation, right? We cannot say that a neural state or a brain state has conscious content depending on some externally defined decoder. Actually, there is only one mapping that is allowed here, and that's the one that corresponds to the experience that the subject has. So we can be a bit more maybe rigorous with defining this idea. So one way to cash out this philosophical assumption that my following work is based on is narrow representationalism. Because you could disagree, right, with this idea that if you have two molecularly identical brains, that they have necessarily the same conscious experience. However, narrow representationalism assumes that they would. So the idea behind representationalism is that we as conscious systems instantiate some representational properties. For example, we represent some object in the real world, so that would be the intentional contents, and those intentional contents determine our conscious experience. For example, if a red apple is being represented inside of me, then I will have a characteristic experience of that red apple. And the narrow part in narrow representationalism basically says that these representational properties are completely determined by our brain states. So it doesn't matter what's happening outside of our heads. If we have two molecularly identical subjects, they will instantiate the same intentional contents, and thus they will have the same subjective experience. So because the neural state completely determines the intentional contents, we can also phrase this as it unambiguously represents the intentional contents. And I think that's a very interesting constraint for a representation to have. Again, if we put it next to bit strings where we don't have this unambiguous mapping. So maybe to be a bit more precise about what I mean with ambiguity, so one way we could sort of formalize this using mathematics is as entropy. So I will define ambiguity here as the entropy, the conditional entropy of all possible interpretations given a certain representation. For example, the representation could be a neural state, and the space of interpretations could be the space of all possible conscious experiences that a human could have. So, in this sense, a high ambiguity, a representation with high ambiguity, has a uniform or a close to uniform distribution of possible interpretations, right? Intuitively, this makes sense because that means that we don't have any information about what the representation is about. On the other hand, if the probability distribution of the possible interpretations given a representation is very narrow, so if it's very specific, then we have a low ambiguity representation. And the idea is that we have all kinds of representations in our world. For example, bit strings would be very ambiguous, so they would be on the left hand of the spectrum. And conscious brain states, as I have argued, given the assumption of narrow representationalism, would be completely unambiguous, or at least, be partially unambiguous. So there's maybe there's an open question there of whether they have to be completely unambiguous and what does it mean to be absolutely unambiguous. But I would say we can definitely make the claim that they are not maximally ambiguous, such as other representations. And then we might have some in between representations in terms of ambiguity. For example, I'm thinking of the example of a dictionary. So on the one hand, you could say, a dictionary alone is ambiguous because if you don't know the language, the words would not make any sense to you. However, if you take more of a structuralist approach to linguistics, you might actually disagree with that statement. You might say that even if you don't know the language beforehand, given all the relationships between the words that the dictionary shows to you, you could reasonably restrict the meaning of certain words. So by virtue of a word taking up a slot in a relational structure, it would basically become a bit less ambiguous. And so I think we can kind of similarly think about different types of neural networks. So some neural networks might represent information in a completely ambiguous fashion, whereas other neural states could unambiguously encode intentional contents. And again, the idea would be that conscious brain states would have to be on the right side of the spectrum. And this is where we get to the experiment that I conducted. So imagine a MNIST classifier. So here, this is a very standard, model in introductory machine learning classes. So we give a image of a handwritten digit to a neural network, and we train that neural network to have high activity at the neuron whose index corresponds to the number which is represented by the input image. So essentially, if we give the network an image of a 2, we want the third neuron to light up, the third because we're indexing starting at 0. So in this sense, when we ask the question about what does this neuron represent, this is quite easy to answer if you know how the network was trained, because you knew that the way you trained the network is such that this neuron should have a high activation whenever you give it an input of the digit 2. So in that sense, this input represents the abstract concept of the digit 2, you could say. Similarly, you know that this neuron right here was hooked up to the top left pixel of the input image, and in that sense, the representational content of that neuron would be the top left input pixel, or if we want to frame it maybe in more phenomenal consciousness terms, maybe the representational content of this neuron would be the top left position in your visual field. Although I don't want to make any claims about MNIST networks being conscious. But now, the question I want to ask is, what if you don't know how this network was hooked up to the outside world when you trained it? So let's say I give you a network with the same size, same number of neurons, same architecture, but I scramble the neurons in each layer so that you will not know by using the index of the neuron what it represents. So for example, if you look at the right side now, the output neurons are not ordered by their class index. Similarly, the input neurons are not ordered in any systematic fashion. So for example, now here, the top left pixel is represented by a neuron which sits at a completely different place in the network. And yeah, again, on the right side, you see that the class IDs of the output neurons are completely shuffled. So if I ask you, what does this neuron represent? Or maybe more specifically, which input pixel position does this neuron represent? Or which MNIST digit class does this neuron represent? Could you figure this out? And my thinking here is that if this neural network unambiguously represents these concepts, then yes, we should be able to figure this out. If not, if we cannot figure this out purely based on the network connectivity, then we can say in any meaningful way that these representations are not ambiguous. So in that case, they would be unambiguous. So I want to operationalize this in an experiment where I take such a network where I don't know how the neurons are ordered in each layer, and I try to decode the representational content of that neuron. And I do this using an intermediate structure, namely a relational structure. And this relational structure captures relations between neurons. And this idea of determining representational content from a relational structure is deeply tied with structuralist ideas in the study of consciousness. So the idea is that while one representation or one neuron does not have any discernible meaning on its own, it might get its meaning from the relationships it is embedded in. So for example, let's say I want to figure out the representational content of the neuron at this position. I will then extract a relational structure that embeds this neuron in a meaningful context. And then from this, I try to decode what its representational context is, content. So let's first look at this extraction step. So I would say this is quite straightforward, and I'm gonna actually make this task a bit harder than described earlier. So in addition of just scrambling all neurons in each layer, I will actually restrict myself to only look at the immediate neighborhood of a neuron, meaning its layer. So I will not consider neurons and weights from previous layers. I will only consider, for example, in the case of output neurons, the incoming weights of this layer. So I look at the incoming weights of each output neuron, and I create a vector out of them. So this means that each neuron gets assigned a vector which has length of the number of neurons in the previous layer. This is nice because it puts all output neurons in a shared vector space, which means I can extract a relational structure by looking at how similar they are. And I do this using cosine similarity, which gives me a matrix. And that's basically the relational structure that I use. Then I take this relational structure and I try to decode representational content. And here I use two methods for doing that. The first one is a bit more direct. I will call that geometric matching. And the second one is a bit more of a black box method. And that one is based on machine learning techniques. So in the geometric matching approach, what I do is essentially I take a reference network. So I take a network where I know what the neurons represent, and that was trained on the same data set, and I create a relational structure out of it. I do the same for my target network. I create a relational structure out of it, but in the case of the target network, I don't know what the nodes of the relational structure represent. So now I take my reference structure and I try to find the best way to align the two. You can think about that as taking two shapes that might not be exactly the same shape, but I try to put them over each other in a way where they overlap as much as possible. In more technical terms, I basically find a assignment of each node in the reference to each node in the target that minimizes the difference in the relative distances between the nodes, between the two relational structures. In the case of the machine learning approach, I basically provide a lot of pairs of relational structures with associated representational contents to a machine learning decoder. And so I train this decoder to predict the representational content from the relational structure. And then I use this decoder on unseen relational structures, or basically relational structures of networks that I have not trained the decoder on. So let's dive into the first results. And actually the first results were already quite interesting. So the first takeaway here is that we actually can decode the class identity of output neurons purely based on their relative position in this geometry that is created by the relative distances between all these output neurons. So I have three decoding accuracies here. The leftmost one corresponds to trying this decoding task on an untrained network. So the network on the left here has not been trained. And here we basically have roughly a accuracy of 10%, which corresponds to what we would expect from random chance. So this checks out and is a good control for our method. Then what's interesting here is we try two different ways of training this MNIST network, and it turns out we get vastly different decoding accuracies. So if we just train using normal backpropagation, and again, I'm talking about training this underlying network and not the decoder. So here actually we don't use any trained decoder, we just use this simple geometric matching technique that I described earlier. So if we train this underlying network with backpropagation, then we get more or less a 40% decoding accuracy, which is already much higher than random chance. So there's already a sense in which the way that our network connectivity represents class identity is not completely ambiguous. But if we train our MNIST classifier using dropout, this shoots up to 100% decoding accuracy. So this is especially interesting because the two underlying MNIST networks, one trained on backprop and one trained on back propagation with dropout, actually performed virtually the same on the MNIST classification task. So we can have extremely different degrees of ambiguity depending on how the underlying network was trained, which is independent of its task performance. But let's also look at our input layer. So here we can ask what position does a given input neuron represent? And here again, just to be clear, we assign each input neuron to one of the pixel positions in the input image. So to make the task a bit easier for the decoder, instead of completely decoding the exact coordinates of the input neuron, we try to decode the distance from the center of that input neuron. And here we use the machine learning approach. And the reason for that is that the geometric matching approach is quite brute force in nature. So we try out all possible permutations of matching the reference geometry to the target geometry. And so that works if we have simple relational structures. So in the case of this experiment, we have 10 nodes. But here we have, I think it's 784 input neurons. So to try every possible permutation here would be completely infeasible. That's why we use this more black box method of the machine learning approach. And actually, we get very similar results in the sense that for the untrained networks, we basically get accuracy that matches random chance guessing. So here we're measuring the variance of the target variable, which is the distance from center, that we can predict. So this is a regression task, and that's why here we measure the accuracy of the decoding with a different metric. And we can see again that we get much, much higher accuracy, or in this case, R2 score, than random chance. Interestingly, here the situation looks to be flipped. So the dropout trained networks are a bit harder to decode than the standard backprop ones. I don't want to get into basically too much speculation as to why we see that difference. I think here the intuition is much easier to get. So if we train this network with dropout, we avoid these single neuron pathways where the performance of the network is defined by a sparse subset of the neurons, and we force the network to represent information using population activity. And if we do that, we encourage the network to learn meaningful representations, in the sense that if two representations are close to each other in the space of these activations, then they are also similar, likely, because there's an overlap in features that they use. But I don't want to get too much into this. I think the main takeaway here is that this works quite well, depending on how we train the underlying network. So can we conclude from having a 100% decoding accuracy that we get basically zero conditional entropy, or in our definition here, zero ambiguity? No, we cannot do that. And the reason for that is that a lot of context is baked into our decoder. So our decoder, both in the machine learning case and the geometric matching case, basically leverages information that we bake into it, which is information about which data set was the underlying network trained on, which network architecture was it trained on, and what subset of neurons are we trying to decode, right? So these are all things that implicitly, by training our decoder or by priming it on some reference networks, we're implicitly giving the decoder this type of information. And if a representation were completely unambiguous, then we would have to be able to infer all of this from the representation. But I'm going to present two additional results here that I think point into the direction that this is not a fundamental limitation of this approach, but more of a practical one. So, for example, let's consider this fact of network architecture. So in the results that I showed before, the reference networks were always based on the same architecture of the target networks that we try to predict representational content for, right? So in that sense, we provide the decoder this information for free. But I tried different combinations of network architectures for my reference and my target. So here, basically, I try different numbers of layers and different numbers of neurons within each hidden layer as my reference, trained on the same task. And using those references, I try to predict the representational content of my target architecture. And again, I use the same three architectures. And we can see that even if the reference architectures differ from the target architecture, we can still get, in many cases, 100% accuracy. In the worst case, we get 75% accuracy, but that's still much, much higher than random chance. So it really looks like this relational structure transcends different network architectures. And then secondly, while again, we do provide the decoder with the information of which data set did we use for free, in a sense, by only fitting it on networks that were trained with this exact data set, right? So our decoder only ever had to consider networks trained on MNIST. It is actually possible from the relational structures of the networks to infer what data set was used. So here I trained two sets of networks on two different data sets. So the networks had the same architecture, but they were trained sometimes on MNIST and sometimes on fashion MNIST. And I trained a classifier to distinguish if a relational structure was obtained from an MNIST trained network or from a fashion MNIST trained network. And actually, depending on how these underlying networks were trained, I'm able to do this with virtually 100% accuracy. Which means that while yes, in the previous results, the data set was kind of assumed in the decoder, we can see that we can also infer this data set from the relational structures. Of course, here the task was not to infer the data set from all possible data sets, but this indicates that in theory, the information of what data set was used was also contained in the network. To summarize these last two experiments, while yes, it's true, we're baking a lot of assumptions into the way we train our decoder, it is also true that things like network architecture are not as relevant as we may think, and things like which data set the underlying network was trained on can actually be inferred. So, for example, you could say that as opposed to being conditioned on, the data set could actually be part of the interpretation that we can extract from the representation. So to tie things back to consciousness, we discussed in the beginning this idea of a neural state unambiguously representing some contents, semantic contents, intentional contents, whatever you want to call them. And those then in turn, according to a representationalist view, would determine your conscious experience. And maybe one way we can again use existing concepts from philosophy of mind is this idea of impure representationalism as formulated by Chalmers. So the idea of an impure representational property is the property of representing a certain intentional content in a certain manner. And in a way, you could say probably most representationalists would be impure representationalists, in that there's probably no one that would say any representation means that consciousness is instantiated, right? They would probably all agree that it has to be a certain kind of representation. So we could cash out this ambiguity constraint or unambiguity constraint as a form of impure representationalism. So at least one way that representations have to be, so the manner in which intentional content has to be represented, is that it is represented unambiguously. And I would say this constraint actually emerges naturally from the definition of narrow representationalism. And the experimental framework that I outlined before and the results for which I presented, I think provides a way, or at least points into a direction of a operational way to determine whether a representation is ambiguous or not. And in addition to that, it might actually open a window into accessing not only the not only the level of consciousness, which is what a lot of current theories of consciousness try to measure, but also it might allow us to get a handle on the actual contents of consciousness. So to summarize this whole project, I think we can determine this unambiguity constraint on representations which are involved in subjective experience. And again, I would say this comes out as a corollary of narrow representationalism, but actually we don't even have to invoke narrow representationalism necessarily. I would say basically the assumption here can be more simply stated as consciousness being an intrinsic property. Actually, for example, if we want to use the vocabulary from integrated information theory, I think the whole assumption of my work resonates with the information and intrinsicality ideas from IIT. So we could say a conscious experience is intrinsic and it's informative, and thus a neural state has to unambiguously define what that conscious experience is about. So that's just to say that we don't necessarily have to take explicitly representationalist view here. Then I would say the next step here of this project was to formalize ambiguity as conditional entropy. And then again, we designed this experimental paradigm for determining whether a representation is ambiguous or not, at least given the context that we bake into the decoder. And there's also a mathematical formalism that shows how we can go from decoding accuracy to a reduction in ambiguity, which is to say a reduction in the conditional entropy that I explained before. But I would say it's quite intuitive, right? If we have a decoder that successfully is able to decode the intentional content from a representation, then we need, right, by necessity, we are in a low entropy situation because we can restrict the probability space, right, using our decoder. assuming that this decoder is actually accurate. Yep, so here's some references. So I didn't really have a lot of references, I guess, in my presentation, but these are definitely papers that have inspired my thinking and kind of shaped how this project went. And yep, that's it